Hello, good afternoon, and this is the second class. Last Saturday, I have left my lecture along with the three videos. Hope those videos have given the elementary idea of understanding interference of light, the concept of wavefront, primary, secondary wavelets, and particularly if you understand Young's double slit experiment properly, this forthcoming Fresnel's biprism experiment can be easily you can understand. So interference, as I mentioned, due to superposition of two or more light waves superimposing one another in the region of superposition, there will be redistribution, modification in the redistribution of intensity of light. The resultant waveform will have amplitude or intensity entirely different from the component waves. The waves which are arriving in phase, there will be increase in intensity and hence amplitude. Such interference is called constructive interference. In that region, you will observe a bright fringe, bright band, and the waves which are arriving out of phase, there will be reduction in intensity and hence amplitude. Such a interference is called destructive interference, and appearance a black band, a black region. So whenever you have interference alternately placed bright dark bands, you will observe. That's what you understood from Young's double slit experiment and the expression for fringe width. So fringe width is thickness of one fringe. Thickness of bright fringe is same as thickness of dark fringe also, because for every bright fringe which occurs between two dark fringe, or the dark fringe is present between two successive bright fringe, they are equidistant, having the same thickness. So let's take Fresnel's biprism experiment. From here afterwards your syllabus commences, and Fresnel biprism, as far as university examination is concerned, it has been asked in 5-mark category as well as 10-mark category. Based on the allotment of marks, you have to plan precise your answer. As I mentioned, I have shown in a photograph about the Fresnel biprism, which uses the second category of interference, because interference can take place either by division of wavefront or by division of amplitude. So Fresnel biprism and Lloyd mirror, they are the examples of division of wavefront category. So wavefront from the source divided into two parts, either by using concept of refraction, reflection, to produce two coherent interfering beams. So these beams are made to travel unequal distance to unite at some angles to produce interference fringes. That's what the concept called division of wavefront. Whereas division of amplitude, in which amplitude of incident beam is divided into two or more parts, either by partial reflection or refraction to produce two or more coherent interfering beams, and the beams travel different paths and reunite to produce interference fringes. You have Newton's rings and Michelson interferometer, and most of the thin film interference, the appearance of colors on the surface of oil spilled on a wet tar road. You have seen very fantastic event you have witnessed here and there. So they are all the division of amplitude category. And coming to Fresnel biprism, as I mentioned, it is an optical device used to obtain two coherent sources from a single source by refraction. Essentially, it consists of a combination of two acute angled prisms which are placed base to base. I mentioned in practice, we never join two acute angled prisms base to base. We used to obtain the biprism just by taking a transparent plain glass plate with proper grinding and polishing. The angles are made, particularly the refracting edge is obtuse angle, which is 179 degree, and other two edges will have angle half degree each, that is 30-minute. And the action of the prism is to produce two coherent images of the given slit, and you know the meaning of coherent. Those coherent images will act as coherent sources which are producing the waves of same amplitude, same wavelength, same frequency, in the sense the same color also. So they are separated at a certain distance. They will have a constant phase difference also. So the idea of using Fresnel biprism is to obtain two coherent sources. The experimental setup, this is 179 degree, so this is a refracting edge that should be mounted towards the slit, and behind this single slit you have a monochromatic source. This is actually slit, okay. So wavefronts coming from the slit fall on this obtuse edge, then they get refracted, in fact they get reflected so as to, that is from this polished surface and this polished surface, and two virtual slits, two virtual images of this single slit appear to come from. That's what the meaning of virtual. So S1 and S2. The separation between these two virtual sources is small d. I will explain how you have to measure this small d. And separation between the single slit and the position of the biprism is taken as a small letter a. And this is a screen. In the actual experiment, the micrometer eyepiece will serve as a screen. The distance between biprism and the screen where you are placing is taken as a small d, and the total distance between the slit and the screen, that is micrometer eyepiece, is taken as capital D. Therefore, capital D is equal to sum of this small a and this small b. So while solving problems, carefully you have to read the data given to you. Sometimes this data will be given and this data will be given, okay. In solving problems, this a and b separately will be given, but in your formula of fringe width you have to make use of this capital D. So capital D is sum of this small a and small b. So this is experimental arrangement, and the wave coming from S1, they get slightly refracted with the help of this phase, and bending in the downward direction, whereas wave fronts which are coming from S2 through this polished surface, they slightly bend, get refracted and moving in this direction. So you are observing two triangles S1, B and E, and S2, and this I have taken as A, and this is E. This is S1, B and E. So this triangle, this triangle. So this is a shaded portion you are observing, that is between B and C. You have a patch of light. So this is a region where you will find the alternately placed interference pattern. So within this region only you are going to get the interference pattern. So I'll just explain the experimental arrangement. So you just remember the diagram. As I mentioned, S is a narrow vertical slit whose width is adjustable, as you have seen in the collimator section of spectrometer while performing experiment in the third semester. And this slit is illuminated by monochromatic light, preferably a sodium vapor lamp, which gives yellow color, and light from S is made to allow to fall on the biprism, which is kept in object holder with a small separation between the single slit, that is A. So in actual experiment it is about 5 to 10 centimeter distance we used to keep on optical bench. So the first slide which I have shown, and in the previous discussion also I have shown that optical bench. The light emerging from upper and lower halves of the prism appear to start from two virtual images S1 and S2, appear to come from the virtual points S1 and S2, and S1 and S2 they will act as a coherent sources derived from the parent source S. That's what I have mentioned in the previous discussion itself. So if you observe on that optical bench, after this slit you will get a bright narrow single slit, whereas after mounting biprism, if you observe behind this biprism, so at this edge if you put and if you move your eye to and fro, you will observe that single slit appear to become two virtual coherent sources. You will observe with naked eye, you can observe two closely spaced vertical sharp slits S1 and S2. They are serving as a coherent sources. In the examination, if theory of biprism is asked, you have to carry out the mathematical manipulation. Of course, the same expression what you have seen in Young's double slit experiment at PU2, the same expression you will get. The calculations also you have to follow in the similar sense. So for theory, let us consider the light emerging from S1 and S2, which are virtual sources in case of biprism, whereas in Young's double slit experiment, S1 and S2 are the double slits which are placed in front of a single slit, and these light waves, they are in phase, they are coming from S1 and S2 in phase. So they are secondary wavelets we used to call. Since they traverses slightly different paths in reaching point P, so there arises a path difference and hence a phase difference. So after refraction through the biprism, the waves which are coming from S1 and S2 in reaching the screen, where I have shown in this diagram. Actually this is a region of interference, just for your understanding sake it has been enlarged. So I have taken point P at a distance x from the center of the fringe pattern. So O is midpoint of the fringe pattern. Just for understanding sake, the diagram is enlarged and this point P is within this region of interference pattern. Okay. So to reach point P, waves coming from S1, they travel a distance S1 P, whereas the wavelets which are coming from S2 to reach point P, the distance traveled is S2 into P. So paths are slightly different. So the waves in reaching point P, okay, they are taking a different paths, therefore they will definitely have a path difference or a phase difference. To calculate that, what I did, I have drawn one perpendicular S1K. So this is 90 degree. So S1K is perpendicular drawn to the path S2P. So K is foot of the perpendicular. So after this perpendicular which I have drawn, the waves from S1 and S2 both will have the same distance in reaching point P. So the additional distance traversed by waves from S2 is this S2K. So this S2K is only the difference, and we call this as path difference between the waves coming from S1 and S2 in reaching point P. So we have to calculate the path difference S2K. So for that sake, in this diagram, what I did, the midpoint of O, and here between S1 and S2 I have taken point Q. Distance between S1 and S2 is small d, whereas distance between S1 and Q is d by 2 and Q to S2 is small d by 2. Okay. So from Q they are at equidistant, and I have taken this angle as theta. We can show this angle, that is S1 P, and you can call it as in this diagram I have taken A in this diagram I have taken this as A, B, R, C, E, right. So with respect to that diagram, we are taking the theoretical part. So I will explain with that diagram only. So we can show this is equal to theta, this is equal to theta, this is also equal to theta, because they are all parallel to one another, and this is the same angle, and this is the same angle. Okay. So in this triangle S1, K, S2, so this is theta, just using knowledge of trigonometry, very small angle. So S2K becomes opposite side, and this is adjacent, and this is hypotenuse. So sin theta is equal to S2K, that is opposite side, divided by what? Hypotenuse S1, S2. So S2K divided by D is equal to sin theta. Therefore, the path difference S2K is equal to D sin theta, and the total distance between the sources, in fact S is also in the same position, and the screen is a capital D. So I have worked out path difference in the beginning. So path difference between light emerging from S2, S1 in reaching point P, as I explained in the diagram, it is S2 into K, and how this S2K is equal to D sin theta in that small triangle S1K, S2, I have defined sin theta. So sin theta is opposite by hypotenuse. So S2k divided by S1 S2. S1 S2 is nothing but small d. Therefore, S2k is equal to, after cross multiplication, it is d into sine theta. That is the path difference. Since that angle theta is very small, so from knowledge of trigonometry, again sine theta is equal to tan theta. So in place of sine theta, I am replacing it by tan theta. That will become d sine theta is now written as a d tan theta as a path difference. So again, referring to the figure in the triangle OPQ. So in the triangle, this is O, this is P, and this is Q. So this triangle, again it is a right angle triangle only. So this is angle theta. I am defining tan theta. So for this theta, this is opposite, this is adjacent, and this is hypotenuse. I am defining tan theta. So tan theta is equal to adjacent by hypotenuse, that is OQ divided by QP. No, sorry, OP divided by OQ. So opposite by adjacent. OP is the opposite side, which I have taken distance as a x. Okay, and OQ is capital D, opposite by adjacent side. So x divided by capital D. So if I replace the value of tan theta in the path difference, so path difference is usually denoted by a symbol delta. So this delta is equal to, so d as it is, in place of tan theta, it is x divided by d. So xd divided by capital D is the path difference. So this is a very important equation. For this equation, since in Young's double slit experiments, you know the condition for constructive or bright fringe, which is integral multiple of wavelength, that is n lambda, where n takes the values 0, 1, 2, 3, 4, etc. And for destructive or appearance of dark fringe, the condition is what? The path difference must be odd multiple of half the wavelength, that is lambda by 2, 3 lambda by 2. Likewise, for that 2n plus 1 times lambda by 2, where n is an integer, again it takes the values 0, 1, 2, 3, etc. So odd multiple of half the wavelength will give you dark fringes, and integral multiple of full wavelength n lambda will give you bright fringes. So since I have taken small d as a separation between coherent sources S1 and S2, and capital D the total distance between screen and coherent sources on which the interference pattern is observed. Let's put the condition for bright and dark. So if you observe the fringe pattern, this is appearance of alternately placed dark, bright. So thickness of one fringe, in the beginning I mentioned it is represented by beta. So separation between consecutive bright, one gap, and another bright, it will be two fringes. So in that case it will become 2 beta. So thickness of dark fringe is same as thickness of bright fringe also, because between two bright fringes, if you measure, you will get thickness of a dark fringe, and if you measure separation between a dark and the next dark, you are getting thickness of a bright fringe. Both are the same. Okay. So let's use a condition for bright fringe, which is integral multiple of wavelength lambda. This is path difference. If you want to express in terms of a phase difference, you know for a path difference of lambda, there is a phase change of 2 pi radian will take place. So 2 pi n will become phase difference. Most of the time we are using the path difference in wave optics. So I am using this equation. So path difference is n lambda, but whereas for the present case the path difference is xd divided by capital D. So I should equate these two. So n lambda from Young's double slit experiment. That's what I have given a video of Young's double slit experiment in the previous class, and I have mentioned about this condition for bright fringe also. So this n lambda is equal to the path difference in the present biprism experiment, xd divided by capital D, where n is taking the values 0, 1, 2, 3, etc. So x, what is x? X is the distance between center of fringe pattern and the point P. So at that point P, I have taken, you can take a position of a bright fringe or a position of a dark fringe. Now we are working out taking a condition of a bright fringe. So point P is position of one particular bright fringe and its distance from center of the fringe pattern, that is O, is taken as x. Therefore, on cross multiplication, x is now equal to n lambda, and this capital D is coming on right side. So n lambda capital D divided by this small d. So this small d should be here. So this is small d, okay, because in some PowerPoint case some Greek letters sometimes misses. If I have used this d, a different small d font, that's what, okay, but this is small d, just next step of this only. So on cross multiplication, this is this small d only, and distance between nth bright fringe. So that n again, it is of a different font that is missing here, but I am explaining this is small n, this is n. So nth bright fringe, because I am just giving the number from center of the fringe pattern. Now the center of fringe pattern is at O, and fringe pattern you have alternately bright, dark, bright, dark. So P is taken as a position of nth bright fringe, okay. Then this distance x will become xn, okay, like that. There are many number of fringes are obtained. I am just taking nth fringe. So distance between nth bright fringe from center O is now given by this is xn. So xn is equal to the same expression, n lambda capital D divided by small d. Let us call this equation as a 1. So those symbols are missing, but I am explaining properly now. Next, the distance between, this is n plus 1th bright fringe. I have taken nth fringe, immediately next bright fringe, n plus 1th bright fringe. From center O, it is now given by, again this is distance. So distance of n plus 1th, this is x, this is n plus 1. The symbol is a problem in a PowerPoint presentation, is now equal to, so in place of n, I have to write n plus 1. So n plus 1 times lambda capital D divided by, this is small d. Let's call this equation as a 2. I will send the notes immediately after the class, at least by unique, so that you can refer. The width of a dark fringe. So width of dark fringe means you have taken nth bright fringe, then n plus 1th bright fringe. Between these two, what is there? There is a presence of a dark fringe. So thickness of dark fringe is nothing but fringe width, okay. So this should be x n plus 1 minus xn. This difference will give you the width of a dark fringe. So that's what I have written here, because between two successive bright fringes there is a dark fringe. So this is thickness of a dark fringe. So this is beta. In fact, this is beta of a dark fringe. Beta is used to represent thickness of one fringe. So beta for dark is equal to xn plus 1 minus xn. It is equal to this is xn plus 1 and this is xn. So, difference between these two, that is n plus 1 times lambda capital D divided by small d minus n lambda capital D divided by small d. So, n times this minus n times this value vanishes, you left with 1 time lambda d divided by small d. So, fringe width for a dark fringe beta dark is given by lambda capital D divided by small d. The same expression you have obtained in Young's double slit experiment also. And now let us take path difference in biprism experiment. This is the path difference x d divided by capital D. Now let us equate this for path difference of obtaining dark fringe, that is integral odd multiple of half the wavelength, that is 2n plus 1 times lambda by 2 is the condition for destructive interference, that is dark fringe. Now this is biprism experiment path difference, means if I take point P, appearance of a dark fringe from point O, again the same x is the distance. So, x is the distance of a dark fringe from the center of a fringe pattern. Again n is taking the values like this. So, if you put these values, you will get lambda by 2, 3 lambda by 2, 5 lambda by 2. So, odd multiple of half the wavelength, that is the condition for dark fringes. Okay. So, x is now equal to, after cross multiplication, 2n plus 1 lambda, this capital D is coming to right hand side, divided by this small d is coming here. Okay, that is the font difference that is not appearing here. This is small d. So, distance between nth dark fringe from center O is given by xn. Same calculation what we did in the previous case. Now, this is 2n plus 1 lambda d by small d. Similarly, if I take immediate next dark, it will become n plus 1th dark fringe. So, x n plus 1 is equal to, so 2n plus 1 already there, you have to add the next fringe, means plus 1 lambda capital D divided by small d. Let us call this equation as 5 and this as a 4. So, between two consecutive successive dark fringes, you have presence of a bright fringe. So, I am calculating the width of the bright fringe is xn plus 1 minus xn. Again I am writing the reason, because between two successive dark fringes there is a presence of a bright fringe. So, thickness of a bright fringe is again thickness of one fringe, that is fringe width beta bright is now equal to the difference between right hand side of equation 5 and right hand side of equation 4. So, what is happening? So, 2n plus 1 lambda d by small d, this is positive and here this is negative, they cancel. We left with what? 1 into lambda d divided by small d. So, again this is the fringe width. So, from equation 3 and equation 6, it is very clear whether you take the case of a dark fringe or a bright fringe, the fringe width is the same. That means all fringes are of equal width. Therefore, beta is equal to lambda capital D divided by small d. This is beta is equal to lambda capital D divided by small d. So, small d is separation between the virtual coherent sources S1 and S2, capital D is the separation between slits S1, S2 and the screen where you are observing the fringe pattern, and lambda is wavelength of monochromatic source used. So, beta is thickness of one fringe. So, theory of biprism means you have to stop at this stage, that is expression for fringe width beta, right. Whereas if experiment is asked where you have to determine the wavelength lambda using biprism, it is clear from the expression for fringe width beta is equal to lambda capital D divided by small d. If beta, because you have involvement of 4 quantities beta, lambda, capital D and small d. Now you have to determine lambda. So, lambda is equal to, after cross multiplication, this small d multiplied by beta divided by capital D will become equal to lambda. So, in this experiment you are determining wavelength of monochromatic light source using biprism. So, if 3 quantities are known to you, you can determine wavelength of the light. So, the experimental part, the very first slide, if I recall, it consists of a long bench, we call it as a optical bench. Here this is a monochromatic source which is fitted inside, and you have a rectangular slit. So, from the slit the light is coming, and here in total in this particular bench you have 5 stands are there which are upright. Okay. So, this is first stand, this is second, and this is third and the fourth and the fifth, and this is not at all required, just one convex lens to intensify the light coming from the slit to fall on the biprism. This arrangement is there, but normally the 4 stands will be there. The first one, the narrow slit, the width of the slit is adjustable. The second one is object holder, where we are mounting biprism here with refracting edge parallel to this vertical slit, and care should be taken all these stands should be at the same height, and they should lie along the same line. Okay. And this is a lens holder, that is a third stand, and a fourth stand is the micrometer eyepiece, where you are watching and you are measuring the thickness of one fringe. Okay. And all the accessories, they are also provided with lateral scales. So, lateral scales means what? These are movable on the all along the length of this bench. Okay. And you can find a scale provided for each stands. So, 0 of this is adjusted to one of the divisions. So, apart from moving these in horizontally, that is along the length of optical bench, they are also provided with movement in a transverse direction, that is perpendicular to length of the optical bench. So, screws you are observing, if you rotate this, you can move this left, right perpendicular to length of this. So, in those scales also you have to make them to positioned at 0, because there also you have a graduated scale. So, 0, 0, 0, so that they lie along the same line. Since you will find all these are circles, circle, 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 circle. So, they should be concentric, they should be collinear. Okay. So, that is what the preliminary adjustments you have. Okay. Let us give the description of the experiment. In fact, experiment is there in the list of experiments in the university, but you are not performing in the list, we have not included. So, experiment I should explain, and that too in a virtual classroom. At least in a classroom I could have drawn and I could have shown biprism passing one by one to your hands, right. Okay. I will try my level best to explain the experiment here. So, it consists of a good optical bench with 4 stands. The first carries an adjustable slit, the second a biprism, the fourth one is a eyepiece, the third one is a lens. You have to introduce a lens in between the experiment to obtain diminished and magnified images of the virtual slits. Through those observations, you can determine the separation between two coherent virtual sources, that is small d. The biprism slit and the eyepiece can be moved in their plane and also at right angles to the length of the optical bench. That is what I have mentioned. They are provided the provision to move in a transverse, that is perpendicular to length of the bench. The slit is illuminated with a monochromatic light whose wavelength is to be determined, that is sodium upper lamp, which has two wavelengths, 5890 angstrom and 5896 angstrom. Since mean of those two values is 5893 angstrom, that is a standard value. So, mean wavelength of sodium light you have to determine in this experiment. So, the slit is narrow, adjustable, and the biprism and the micrometer eyepiece, they are all mounted on the uprights and adjusted to be at same height along a straight line. The slit is made vertical and parallel to refracting edge of the biprism. As I mentioned, the line joining the slit and the biprism must be exactly parallel to the length of a optical bench, otherwise you will get the problem called lateral shift. I will explain what is lateral shift. That is a technical problem. When you are performing the experiment, you may face that problem. So, as you mounted and behind the biprism, if you notice, you will get two virtual narrow slits of the slit kept in front of the monochromatic light. In the eyepiece, if you move the biprism, what you are observing, just after putting this you will not get fringes, because the prism has to be rotated in its own plane. Okay. There is one fine adjustment screw is there. By rotating that through small angle, now vertical slit is parallel and refracting edge of the prism is also parallel, that is vertical. So, just slight rotation of a biprism which is in line with the single slit will give you appearance of a bright patch in the field of view of a eyepiece. So, that should be obtained in the middle. After working on the fine adjustment screw through a small angle, you are rotating the biprism, the fringe pattern will be obtained. So, fringe pattern will be sharp and clear as you work on the fine adjustment screw. I will show what type of screw it will be. So, it is illuminated the light from monochromatic source. It has the prism is capable of rotating in its own plane. So, when biprism is moved along the optical bench till on looking through it along the axis of optical bench, two equally bright vertical slit images are seen. Then eyepiece is moved till the fringes appear in the focal plane of the eyepiece. I mentioned about lateral shift. So, in the micrometer eyepiece you have a vertical cross wire. After obtaining a clear pattern of the fringe pattern, you just coincide the vertical cross wire on a dark fringe. Then put your left hand with thumb somewhere around 65 centimeter and forefinger at 50 centimeter. Now, the eyepiece I mentioned it is a scale, you just put it at 65 and put your thumb there. Now, after coinciding vertical crosswire with a particular dark fringe, just observe through the eyepiece moving this eyepiece from 65 centimeter to 50 centimeter in a difference of 15 centimeter in a forward direction. Observe whether the vertical cross wire which you have coincided on a dark fringe, will it remain on the same dark fringe? If it remain on a same dark fringe throughout the branch, there is no lateral shift. In the forward direction also you have to observe, in the backward direction also you have to observe, that is while moving it in a backward direction from 50 to 65. But sometimes what happens in a movement of 15 centimeter either forward or in backward direction, sometimes the vertical cross wire of your eyepiece, it shift either on left side or on right side depending upon whether you are moving in forward or backward direction. Some number of fringes are crossed. You have to count such number of fringes. For example, from 65 to 50, if dark fringes which are crossing the eyepiece, if they are 4, in the same, if you reverse, that is from 50 to 65 you are moving in backward direction, again if you observe the same 4 fringes will be crossing the cross wire, then the lateral shift is equal to 4. So this is a technical error. The reason for that is I mentioned the vertical slit in front of the source is kept parallel to the biprism refracting edge. The line joining biprism with the vertical slit must be exactly parallel to the length of a optical bench. If they are not properly set, this technical error will be appearing. Of course, you have to remove this lateral shift. There is a simple procedure. So in a forward movement, if fringes crossed is 4 either on left or right depending upon, then after reaching 50th centimeter, what you have to do, I mentioned there is a transverse scale provided to the biprism stand. You have to work on that screw so that cross wire is shifted opposite side. For example, from 65 to 50, if 4 fringes are crossed to left side, after reaching 50th centimeter, work on biprism transverse scale in opposite direction, shift 4 fringes to the right. Okay. Then when you are moving backward direction, you will observe the 4 fringes were crossed earlier. With this adjustment, you will observe 3 fringes are crossing. So after reaching the 65th centimeter position, work on eyepiece transverse scale. So in the reverse direction, you are opposite movement of 3 fringes. So opposite to that, you have to work on the transverse scale. Suppose on right side 3 fringes are crossed, now you shift 3 fringes left side. So like this 3 to 4 times you have to move forward, adjust, backward, adjust, first with biprism transverse scale and later with eyepiece transverse scale. So finally you will observe the vertical cross wire will remain on the same fringe, so that the lateral shift is completely removed. So I have given the meaning of lateral shift here. So lateral shift of the fringes should be removed with the help of biprism and eyepiece. The reason for appearance of lateral shift is that the line joining the slit and the biprism is not parallel to the length of optical bench. The bench should not be disturbed once all these adjustments have been done. So it has been asked many times for 2 mark, what is lateral shift? So just you have to give the definition. Shifting of fringes relative to cross wire when eyepiece is moved along the bench is known as lateral shift. You may be moving in forward direction or you may be moving in a backward direction. You are observing some number of fringes are crossing with respect to the cross wire. So such a movement shifting is known as lateral shift. I have explained how to remove the lateral shift also. and where you have to keep the eyepiece. So for that you have to introduce a convex lens in between biprism and the micrometer eyepiece. So you are observing here. So this is your eyepiece. This is a transverse scale, and here this is a transverse scale provided for prism, and this is for eyepiece. So in forward direction, if 4 fringes are crossed left, with the help of this screw, you have to adjust 4 fringes shifting towards right side. And when you are moving in backward direction, after reaching here, if 3 fringes are crossing to the right, with the help of this you have to move 3 fringes left side. Okay, so this gradual nearly 3 to 4 times you have to, sometimes it may be 10 to 15 fringes also crossing. It all depends upon, as I mentioned, line joining this slit with biprism. If it is not parallel to the length of optical bench, this error will appear. You have to remove lateral shift and go for the measurement. Without removing a lateral shift, you are not to proceed further. Now the question is, where you have to keep this eyepiece, at what distance from this single slit. It depends upon, because throughout the bench wherever you move the eyepiece, you are observing the fringe pattern. Only thing is, as you move this eyepiece towards, you are observing the width of the fringes go on increases. Pattern will remain stationary, but because of this, because it is also a lens arrangement, the eyepiece, because of this the magnification of fringes changes. So as you move towards, wider fringes you are noticing. As you move away, you are observing narrowness of the fringe pattern. So the question is, where you have to keep this. So for that you are introducing one convex lens here between these two, without disturbing the position of eyepiece and the biprism. For 2 different positions of the lens, you are observing the virtual sources S1 and S2, once magnified and another time diminished images. So at what position you are able to get both type of magnified images as well as diminished images. So there you have to put this eyepiece for all measurement purpose. That is, suppose if I put it at 75th centimeter, okay, and now if I take a convex lens whose focal length is around 10 or 15 centimeter, for one particular position when it is near, I will get diminished images of coherent sources. Now the fringes disappear only because after putting this converging lens, that is convex lens, you have appearance of only the virtual images S1 and S2. They should be bright, sharp, okay. The length will be lesser to obtain diminished images. Not only length, the separation between them is also very narrow. For another position of the lens, you will get the same coherent sources S1, S2, length large, the spacing between those images will be wider. Okay. So the trial and error basis method, you have to put the position of eyepiece such that with the help of this convex lens, for 2 different positions of the convex lens, you are capable of obtaining magnified images as well as diminished images. So at only one particular position, of course it depends upon focal length of the lens also. Usually if I take 15 centimeter focal length of convex lens, 4 times that you will get the separation between this slit and eyepiece, where you are capable of getting both diminished images and magnified images. Usually separation between diminished images, as I mentioned, narrow, and separation of magnified images will be wider. They are in a ratio 1:3. 1:3, that is 1 mm separation between diminished images, whereas 3 mm separation between magnified images. Okay. So, you have to use this convex lens to obtain diminished and magnified images. With the help of that, you are also measuring separation between magnified images as D1 and diminished images as D2, and the square root of D1 D2 will give you separation between coherent sources S1 and S2. That also I will explain. So, after lateral shift, so position of eyepiece, how you have to decide that I have explained. So, remove the lens which was kept in between. So, again fringe pattern will be there. And now, when the fringes are observed in the field of view of eyepiece, the vertical crosswire is made to coincide with the center of one of the bright fringes. Either you take bright or dark, it is your convenience. The position of the eyepiece is read on the scale as x naught. So, that I am taking it as the first fringe, the position of the first fringe as x naught. So, there I mentioned micrometer eyepiece means least count of that micrometer eyepiece you have to determine in the beginning itself. It is just like a screw gauge, because by rotating the drum you have a pitch scale reading you have to observe. On the drum you have graduated divisions, 100 divisions are there just like in a screw gauge, and a reference mark will be there. Okay. You have to read pitch scale whose least count is least count in the sense value of one division on pitch scale is 0.5 millimeter, and a total 100 divisions are there. So, you have to determine PSR as well as HSR, and you have determined the least count. Okay. PSR plus HSR into LC is the total reading. So, the fringe which I have taken as a first fringe, its position and its reading you have to take it as x naught. Then the micrometer screw of eyepiece is moved slowly, and number of bright fringes, if I take n. In actual experiment what we will do, the first fringe, then I will put it on sixth fringe. So, position of sixth fringe. So, difference between those two readings will give what? Sixth fringe minus first fringe. You will get width of 5 fringes. Next, after sixth, next I have to take 11th fringe, because 11th minus 6, again I will get width of another 5 fringes. So, after 11 you have to move it on to 16th fringe, 16 minus 11, again width of 5. So, 5 fringes reading you have to go on take, and mean of 5 fringes, and divide it by 5, you will get thickness of 1 fringe. That is how you have to determine beta. So, that is what here it is explained. So, after n fringes, again the position of crosswire is again it is read as xn. So, fringe width beta is equal to xn minus x naught divided by n. So, how many number of fringes you have crossed, so that you have to divide here. That is how you have to determine thickness of one fringe. And as far as measurement of capital D is concerned, the reading of vernier on the optical bench corresponding to position of slit and eyepiece are to be noted. Suppose if a slit is kept at 0th centimeter, and the position of eyepiece if it is at 90 centimeter, so 90 centimeter is capital D. So, beta is known to you, capital D is known to you, but what about small d? Separation between slits S1 and S2, that you have to determine with the help of by introducing a convex lens between biprism and a eyepiece for without disturbing the distance between eyepiece and a biprism. For two position of a convex lens, you are capable of obtaining magnified images as well as diminished images of S1 and S2. Fringe pattern disappear on introducing a convex lens between. So, that is the procedure you have to follow here, and it is based on the property of a convex lens, conjugate foci, that is without changing the distance between object and screen. This is your total distance, capital D, right. Now, in this case, what happens? The biprism is here. For first position of the lens, that is towards biprism, in the eyepiece, I am capable of getting magnified images, that is enlarged images. So, length will be larger, the virtual sources, separation is also larger. So, for position L1, so this is a lens, right. So, in this case, the distance between the lens and the source, object distance u you have to take, and image distance is to be taken as v. Now, in this case, our object is this biprism, which is capable of giving the S1 and S2, two closely spaced images, right. So, lens is making those images to observe in the eyepiece. Okay. So, when you are getting magnified images, so this distance u, that is object distance, and this distance is image distance. Whereas, for another position of lens, when it is far away and it is towards eyepiece, for this position, the same magnified images will appear as diminished images, length small, separation narrow. Okay. So, after getting magnified images, what you have to do in the eyepiece, micrometer screw is to be worked, it is moved and coincided to left bright fringe, take the corresponding reading, and the right bright fringe, take the corresponding reading. The difference between those two readings will give you small d1. Similarly, d2 is separation between two diminished images of S1 and S2, that is for second position of the lens. In that case, what actually happens, the earlier object distance and image distance are interchangeable. Okay. Now, this distance will become object distance and this distance becomes image distance. You will observe they are entirely reversed. So, earlier image distance is now becoming object distance. Earlier object distance, that distance is now becoming the image distance in the second case. The actual difference between S1 and S2 is to be calculated using magnified image distance and diminished image distance. Okay. So, that calculation I am showing, you know, for a lens, magnification is equal to what? The ratio of height of the image to height of the object, or image distance divided by object distance. So, that concept you are using now. So, to determine separation between virtual sources S1 and S2, a convex lens of short focal length is mounted between biprism and eyepiece by moving the lens along the length of a bench for two positions of lens L1 and L2 obtained such that enlarged real image of S1 and S2, and for another position at L2 diminished real image of S1 S2 are obtained. So, this is possible only when object and image distances are interchanged, that is conjugate positions, the property of convex lens we are using. So, separation D1 and D2 of enlarged and diminished images are respectively measured, and calculations for first position of L1, image distance divided by object distance is equal to the magnification. So, the separation between magnified images divided by the actual distance small d, that is also what? Magnification, because height of the image to height of the object. So, in this case S1 S2 actual separation is small d, that is height of the object you have to take. So, separation between magnified images as d1, both are equal to magnification m, that is what I have equated these two. For a second position of the lens, height of the image, that is separation between diminished images divided by actual separation between S1 and S2 is equal to image distance divided by object distance. Image distance I have taken as v dash and object distance as u dash, but because of that property I mentioned the V dash is equal to U earlier object distance, and image distance in the second case is equal to object distance in the first case. That is what the interchangeability. So, they are cancelling one another because this V dash is equal to earlier object distance U, this U dash is equal to earlier image distance. So, V with V, U with U get cancels. So, right hand part is 1, but on the left hand part d1 by d multiplied by d2 by d. So, numerator d1 d2, denominator d into d, it becomes d square. So, this ratio d1 d2 by d square is equal to 1. Therefore, d is equal to d1 d2 whole to the power half, that is square root of d1 d2. So, small d is equal to square root of d1 d2. You have to remember this equation also, because some of the problems they are appearing by providing separation between magnified images and separation between diminished images. So, separation between S1 and S2 in the problem he will not give, he will provide the data like this. So, you have to use this relation, separation between S1 S2 is square root of d1 d2, where d1 is separation between magnified images and d2 is separation between diminished images. So, how you have to determine beta, that is fringe width, and separation between S1 and S2, and of course capital D, the total distance between slit and the eyepiece, that is screen. You can substitute all these so that wavelength lambda can be computed, that is calculated. Okay. That is how the experiment is to be performed. And now in this slide, the actual in our laboratory we are having a facility of this type. Ours is I mentioned it is 2.5 meter length. Minimum 6 to 8 persons are required. It is such a heavy sturdy instrument. Okay. Now this is a rectangular box where the source is kept. In front of that you have a narrow slit. The screw you can observe, this is a slit that will serve as S. So, about 8 to 10 centimeter distance, this is an object holder where the biprism is to be placed. So, if you observe behind this, single slit will be seen. Behind biprism, if you observe, you will get a single slit split up into two virtual coherent sources. Right, and this is the lens holder. The lens is kept here. This is a third stand. The fourth stand is the micrometer eyepiece. So, you can observe the transverse screw is provided here. So, these are capable of moving along the length. So, if you work on this, they move perpendicular to length of the bench. Okay. Just a slide I am showing. So, this is a slit, the screw is provided. You can observe rectangular slit. By rotating this, the slit can be closed or can be opened, or you can make it as depending upon your requirement. The width of the slit is adjustable, and you are observing another screw to adjust height of the slit. So, by rotating this, this can be moved in this direction. You can move it up or down, right. The screw to set up slit axis, then it is also capable of rotating in its own plane also, small rotation. Either you can rotate this or the prism holder also you can rotate. This is what the prism holder you can observe. Here also a screw is provided to adjust height of the biprism. You can observe the biprism is kept here with the refracting obtuse angle, which should be mounted towards the slit. Okay. So, these are sliding screws. You can slide this biprism left right. I mentioned after mounting this, if the bright patch is not seen, you have to slide so that the bright patch should be seen within the center of the field of view of eyepiece. And this is what I mentioned. This is a tangent screw to rotate the entire setup. That is, the refracting edge I have to rotate in its own plane, immediately you will get fringes. This is very important arrangement. Okay, and this is a screw what you are observing, the tangent screw, that is a transverse screw to remove lateral shift of the fringe pattern. I have mentioned how you have to remove the lateral shift. Okay, so just a slides I am showing. Now this is the eyepiece which serves as the screen. Okay, so this is eyepiece, and here you have objective. So here also a screw is provided because they are all kept upright, so you can adjust the height of those. All should be at the same height, all should be concentric collinear, and they should be along the same straight line. Okay. Now this is a drum micrometer screw to rotate the micrometer. Okay. Now you can observe, this is what it is written here, main scale reading. It is not main scale, it is a pitch scale. It is a pitch scale reading. On the drum itself graduations are there. The whole arrangement is Ramsden's eyepiece. You have studied in oculars. So this is the micrometer eyepiece. Actually, if you perform the experiment, all you can touch and you can get the result properly, but virtually I am just explaining the experiment. And this is what the slide I have shown previously, the previous class, the biprism, the refracting edge, that is 179 degree, you can observe. So this is the fringe pattern. Of course, wherever you are observing bright, it is yellow color and a dark band. Okay. So depending upon position of the eyepiece, you can observe here bright and bright, that is the indication of virtual coherent sources S1 and S2. If you introduce a lens, immediately fringe pattern disappears, you will get only bright, bright. The lens position you have to adjust such that you should get a sharp real image of S1 and S2. Okay. Separation between them is small d1. For another position of the lens, the sharp, narrow and diminished images you will get, the separation between them is small d2. Okay. I hope you understand this experiment virtually. Okay. I will send you the notes either by evening or tomorrow morning. Okay. Thank you.